Hello, I'm Sandra, and this is Karl. We are from Cybernetica, and we are happy that you are here. We are going to have this nice workshop about space and data, and who sees what in space, what are the data flows, and how things are going. So, firstly, in this presentation, I will be going over what we do in this workshop, who we are, what is Cybernetica, and then I will give over the floor to Karl, who is our brains, and he will explain to you everything about privacy. And then we will do a hands-on group exercise with you. Until then, we are just listening here. Then we will divide into small groups. We will choose those tables here, and Karl will explain everything that we will do, explain the use cases, how privacy works there. Then we start mapping the things out, what are the data, who sees what data, and so on. And then finally, we will try to create together a few visibility tables for you. And finally, we will have a short overview how to achieve privacy in practice. So let's fly away. In Cybernetica, as probably lots of you know, we are considering ourselves as the architects of Estonia. And we work across the globe, creating different mission-critical systems. We were building everything from e-governments to cybersecurity in-house systems. And we have knowledge for almost 30 years, working with private companies and governments. So what we work with, we have different solutions. Of course, nowadays, most popular one is AI and machine learning, but we do hands-on stuff also. We do border and coastal surveillance and different maritime surveillance technologies. In addition, of course, cybersecurity, as I mentioned, digital identity, interoperability, of course, privacy technologies, as is the topic of this workshop, and different R&D. As we go forward, of course, in our house, why we do so many different things, and it comes through deep in tech. So we have our own in-house research institute, which means we are actually accredited research institute. We have scientists working, we have PhD students working, and our R&D team is over 50 people, and we both are from this research institute. As research institute also work in the universities, we work the similar way. We have contracts with European Space Agency, Europe. We have different fundings from NATO, DARPA, European Defence Fund, and so on. Just a short intro of our team. I'm Sandra. I'm the project manager of different space projects. This is Karl. He is the developer in our space projects. Also in this room, we have Catherine, who has been working throughout now from June, I think, also in our space projects as a developer. And we have different consultants who have been working in our projects for over 10 years. And now I will give over the floor to Karl to go to the background, what is actually privacy, so you would know how to work with it in the workshop session.
Yes, thank you. So, as with anything, privacy is somewhat an overloaded term. There is a lot of different ways to use it, different contexts to use it in, even in space. So one big difference is that generally, when we mention privacy, we mean privacy for individuals. There are many laws, both in Europe and in the US and elsewhere. For example, the GDPR here in Europe is one of the better known ones that regulates privacy for individuals. But privacy also applies for organizations. You can consider national secrets or company secrets, commercial secrets, retaining your competitive edge from your other companies. You have NDAs. These all are things that also require privacy, and you need to think about it in terms of privacy. So how privacy actually often is formalized is through privacy goals. So in security, many of you may know is the so-called CIA trifecta, or the confidentiality, availability, and integrity triangle. So these are the three in the red triangle here. But the other side of this are also the privacy goals, the unlinkability, intervenability, and transparency goals. These form the counterpart to the privacy or the security aspects, and you can actually, you have to do trade-offs. You cannot generally get everything at once for all of these goals at once. And how you actually want to achieve these goals is very dependent on your use case. So for example, here in the security trifecta, confidentiality and availability are on opposite sides. This means that you cannot often have full confidentiality or full availability. If you want full confidentiality, then you have no access to data, or if you have access, it's very minimal. You encrypt all of your data and only the people authorized can access it. On the other side, you have availability, where you give that full access to all the data to everyone, and clearly this is directly countering the confidentiality goal. So you can't have two at once. You have to decide or design your systems in a way that if you prefer confidentiality or availability. In the other ones, we have integrity and intervenability. For integrity, we want the data to make sure that the data is always the same, that the processes are always the same, that you can be sure that this data that I send to you is exactly the one that I intended. But on the other side, intervenability counteracts that, where we want the data to be configurable by the data owner directly. So for example, all kinds of cookie banners are intervenability technologies because they allow the user to configure how they want their data to be used. But from the integrity side, you want to make one process and one process only and make sure that everyone uses that process. Then we have the unlinkability and transparency. These are maybe slightly less known. Unlinkability is things like anonymization and pseudonymization, where you try to make sure that any data you have, you cannot link back to the original owner or the data owner. These are also all kinds of black box processes where you don't exactly know what is happening to the data. You try to protect your processes. And this is generally only on a need-to-know basis to who can access the processes and see what's actually happening. On the other side is transparency. This allows for full linkability, who did what happened, what data moved where, when, and so on. This is all kinds of logging and so on. And all of these aspects make up this so-called privacy and security six-pronged star. Now, with all these privacy goals in mind, since, as I said, all of these use cases that we will be thinking about, they require slightly different scales. Some use cases require unlinkability, some require confidentiality. In others, these are very non-important. They need more transparency and intervenability, for example. So how do you actually think about these use cases? We can actually make all kinds of these privacy-preserving solutions, but to do that, we need to actually say exactly what is the problem we are solving, what is the underlying process, so why we are even doing this, why are we using the data, what is our goal, who are the people involved, who are the data owners, who are the data processors, who are anyone else that is impacted by these processes. You need to define what are the exact data objects that are moving. The more granular you go, the better you can design which pieces of data should be protected, which are critical for privacy, which are critical for your actual use case. And finally, once you have all that, you can start thinking about which of these data objects need to be protected. What is the privacy consideration in this whole thing? So as an example, coming from space, the actual project that we at Cybernetica did was a use case where spacecraft owners, spacecraft operators, they need to make sure that their satellite doesn't collide with anyone else's satellite. To do that, you need to compare these trajectories of the satellites and see if they crash or not. There are very many mathematical, statistical methods to calculate this probability, but at the end, this probability is used to then avoid collision avoidance maneuvers to make sure that everything is nice and safe in space. In this system, the main stakeholders are the spacecraft owner and operators, but also the space situational awareness service providers who process the data, who offer the service to calculate everything for you. But there are also all of the other kinds of stakeholders who are tangentially impacted by this use case. For example, astronomers who want the space to be clear. They want to still look out into space, but if everything is colliding, there's a lot of debris, they eventually won't be able to look out. So tangentially, they are also stakeholders in this use case. So it's very clear that this is an important thing to avoid these maneuvers, but sometimes, but to do this, you need trajectory data. This includes the position of the satellite, velocity of the satellite, the uncertainty of how exactly you know where your satellite is, but it also includes future maneuvers, your plans, your mission data. And it needs this for all spacecraft in your nearby orbits. And at the end of this calculation, you get the probability of collision, of course, but you also get the time of closest approach, so you can actually know when this collision may happen. And without these two pieces, the time of closest approach and probability, you can't really make any actionable decisions. But this is a problem because your mission data, your future plan maneuvers, your trajectory data, it may be sensitive. For example, you may try to retain your competitive edge. These might be defense satellites that don't want to broadcast to everyone where the satellite is, in any other kind of places. So there is a very clear requirement to keep this data private somehow. How it is done currently is everything is shared pretty much publicly, and the people who don't want to share, then they will take the public data and do the calculations themselves. But obviously, this is somewhat wasteful, and yeah, it's a problem. As a more down-to-earth use case, we can think about average speed cameras. So there has been some discussion in Estonia about how to combat speedsters, people driving above the speed limit, and one potential approach is to use average speed cameras. So you have two cameras that fix your car's location at the camera, or at the time when you pass that camera, and then you use, if you know the distance between the cameras, you can calculate the average speed of the car driving. If the average speed exceeds the speed limit, then obviously you had to be speeding. Very simple mathematically, and this is could be very easily done if you just have the license plate numbers and the times at this place. But there is also other drivers on the road, people who are not speeding. You have pedestrians, you have law-abiding citizens, you have cyclists, and the system should be designed in a way that their data does not get entered into the system. It's not saved in the system to prevent any kind of tracking in the overall solution. So ideally, you would only need the license plate of speeding offenders and the times at both endpoints of the road to calculate the average speed. But to do that, you actually, in most cases, process also information about everyone else. And this is, again, a bad. So this is where we will now do group work. If you take a look around, you will see there are 4 tables around the room. I would like you to group around those tables in some way, and we will I will ask you to come up with your own use cases, similar to what I described. And it would be very great if this would be a use case from your specific field, but we also have some examples for when you are not, if you cannot come up with one this quickly. So please.
So the tables are here. Where are the white papers? Let's say around 3 people around the table. If there are more people interested in joining the group work, then let's say up to 5. But probably 3 is best for the conversation. So let's stand up, have a bit of moving. Then the legs won't be stiff after this session. You can stand around the table. And if you are finding your 3 to 5 persons to work with, then discuss what we mean about the use case. Use case means that you think about the thing in space where you know that there's data moving. I mean, nowadays, there's always data moving between point A and point B, company A, company B. So think of where you know that in space you have to use data, and some of part of it might be private somehow, or there might be some kind of commercial thing you want to maybe hide from the partner or the other company. You want to share some part, you don't want to share another part. So here are, in the previous slide, were the ideas of different topics. For example, in-orbit fueling, secure data marketplace for Earth observation, collision avoidance, what we talked about, orbit determination from radar data, and so on. But maybe you have some of your own ideas, and then try to define who are the parties there, what are they doing, and what type of data they are using. So this is the next slide.
Try to actually follow these 4 questions or 4 bullet points here. Define what the problem is that you are trying to solve. Who are the stakeholders? What is the data? And finally, what is the privacy consideration there? Why is this current approach maybe not the best in terms of privacy and these privacy goals that I talked about?
And in the meanwhile, we are moving forward. We are going through the tables here, through your groups. You can ask us questions. We will try to move you through the right place. Probably just out of the blue, it's really hard to think of those ideas, but we have ideas of our own. And afterwards, based on what you define here, we will start to creating those data visibility flows and data visibility tables. If you don't get any idea, that's fine also. We have pre-made use cases. But just so you would have the exercise done by step, as usually this type of determination goes for this type of projects. So now I give time to you to discuss, and we will move between the tables for a while. And then, let's say after
10-15 minutes?
15 minutes, we will take the next step.
working out about a couple, 2, 3 things. Picked up my microphone and started to sing. I was feeling worse than the words come out. Fell on some keys, then this song walked out of me. Lost my head, decided we liked it there. Lost my head there. I don't wanna talk about it, yell about it, oh no. Maybe I just wanna sing about it. Lost my head there for a second. Had a little funky psychosis, all sweet relief. I don't wanna sit around it, walk around it all today. So I gone went ahead and just levitated. Lost my head there, oh whoops. Lost my head there again. Didn't wanna mess around, look around at all of it. But then I did though.
So we will soon be moving on. Hopefully everyone have at least an idea of a use case. So try to write everything down that you have. You also can have multiple use cases, but try to write it down, and then soon we will move on to the next step. Okay, so it looks like most of you have already figured out some use cases. So now we will go on to actually map out who sees what data and why. We will do this in two parts. First, I will do with the examples that I showed before. I will go through them again and map out the visibility tables, the initial version. Then you will also do the same, map out the initial versions of these visibility tables. And then I will flesh out these visibility tables in the second half, and then you can also do that the same for your own use cases. Okay, so now that everyone has their use cases, we will go back to our previous ones. So first of all, the collision probability calculation use case, where the satellite owners wanted to see if their satellites are colliding, but we didn't really want to share the trajectory data. And the other use case was the average speed measurement cameras, where the data of law-abiding citizens and other pedestrians and other road users should be not involved in this system. So for the first use case, we have three stakeholders. This is on the left-hand column here. We have two spacecraft owners or operators, and they have information about their satellite. So on the top, we have all kinds of data objects. So we have position, velocity, and uncertainty for spacecraft A, and we have the same for spacecraft B. We also have here an space situational awareness service provider who is offering the service to actually calculate this probability of collisions. So we will mark now X's for who owns the data, who creates the data, who has access by default to this data. So we assume that these spacecraft owners, they will have access to their own data and only their own data. And the same for B. And the service provider, they use this data to then generate these outputs. So since they are the ones who generate the outputs, then they will be the ones who own this data initially. For the other use case, we do a very similar thing. We first, on the left, we have all of these stakeholders in this system. And on the top, we have all of the data objects that are involved in this system. So on the left, we have, of course, a speeding driver, someone who is breaking the speed limit. But we also will have other drivers on the road. I have omitted all the other road users in this case because all their data is not in this sense relevant. It shouldn't ever be seen by anyone. It shouldn't be tracked, so we can omit this part. We also have the police and border guard here. We have both endpoints or endpoint cameras of the road. And finally, we have some kind of server that's actually calculating this information to come up with your average speeds. On the top, we have a whole bunch of different data objects. We have the license plate of both the speeder and the other drivers. We have the time points when they pass this camera 1 and camera 2. We'll label them as time 1 and time 2. And the same for the other driver. Then we have the average speed, of course, as the output. And to do the calculations, we also need to know the distance between the cameras and what the actual speed limit is, so we know when an infraction took place. And at the very end, since the police and border guard will want to enforce this, send out tickets, and since this needs evidence, there should also be some kind of a photo of the speeding driver. Now, this mapping is somewhat subjective. You may, for example, with a photo of the driver, decide that this should be owned by camera 2, since this is who takes the picture, the device that takes the picture. But since it shows the driver, I have put it as the speeding driver's data object. Of course, the license plate is owned by the drivers themselves. The times when they pass the camera, this will be recorded by the cameras. So this is owned by the cameras. And since the server is doing the computation, they will own the average speed. And in the next half, so this is what will you do in a moment. You just map out all of your stakeholders, map out all of your data objects and who owns who, but leave space, because in the next part, we will map out these tables to see who sees what exactly in each use case. And we'll come back to how this is done after you've done your initial mapping. So please, get back to work and make tables. Just a quick clarification as well. Initially, there can be only one X for each data object, so one owner, preferably. Eventually, there will be more, obviously, because everyone sees everything in normal systems. But let's start with just one.
Say a single word. I know just what you're thinking, girl. You don't have to tell me you love me. Take it easy. You don't have to be a movie star. In fact, I want you just the way you are. You don't ever have to change for me. Take it easy. Take it easy. I've been waiting for someone like you for my whole life. I've made a few exceptions on some lonely nights. I'm not proud of my mistakes, no, I'm not trying to fake it. I need you. I don't need you to be on time. All you have to be is mine, oh mine. I don't want you to do anything. Take it easy. You don't have to keep your 9 to 5. You don't have to say exactly why. I just need for you to stay with me. Take it easy. Take it easy. I've been waiting for someone like you for my whole life. I've made a few exceptions on some lonely nights. I'm not proud of my mistakes, no, I'm not trying to fake it. I need you. Waking in the dawn of day, and I gotta think about what I wanna say. Phone ringing off the shelf, I guess it wanted to kill himself. Waking on a pretty day, don't know why I ever go away. It's hard to explain my love in these days. You could say I've been most around, but honey, I ain't going nowhere. Don't worry about a thing, it's only dying
Okay, it seems everyone has the initial table at least somewhat ready. So we can now move on to create the next table to show how this will start, the visibility will start spreading around from these data owners. So first, let's do our example use cases. So first of all, the collision probability calculation. This is the initial table that we had, where each satellite owner had their information, and the service provider only had access to the outputs. Now, from the use case, it's quite trivial to see that everyone sees their own data. The service provider obviously needs all of this data to do their calculations, so they should, in some sense, see it, have access to the location data of the satellite, because otherwise, if you don't know the position, the velocity, the uncertainty, you can't really calculate the probability of collision. You just cannot do the calculation without this. So they have to see all the data. The spacecraft owners should also see the outputs, because otherwise, why would they share the data if they don't get the outputs, if they don't learn what they wanted to learn in the first place? So obviously, they will need to see the time of closest approach. They will need to see the probability of collision. And in order to actually make educated maneuvers to make sure that you're not increasing the risk of collision, they should also get access to the other spacecraft's position. So they can do their own analysis, run their own alternative maneuvers, discuss. So as we see, everyone now sees everything. And this is how it is mostly right now using the current systems, where at the end of the process, everyone has learned everything. And this is not good. But it turns out that using what we call privacy-enhancing technologies and confidential computing technologies, we can actually improve on this. So instead of everyone seeing everything, the spacecraft owners will still see the outputs, because this is the whole reason why we are doing this. But the service provider actually does not ever need to see the whole data. They will still use it, but this data should be protected throughout the process. So here we see I have marked in red with red P's for protected, that these data, while the service provider does have access to them, they are, in some sense of the word, protected. And the position of the other spacecraft should not actually be visible to the other spacecraft's owner. This is a different use case already, but you can actually do maneuver planning similarly to this, where some third party who will use these privacy-enhancing technologies will do your calculation, your maneuver planning for you in a way that all of the process or all the data is protected. So only the data owners will actually visibly see their own data. In the more complicated approach of the average speed cameras, again, you have your data owners who see their own data, or whoever generates the data still sees their own data. But now we can start going one by one to expand these. So again, as with the previous example, the server, in order to calculate things, in order to determine who gets a ticket, who doesn't get a ticket, they need to see everything. This is how it's conventionally done. All the data gets aggregated in some database. The server takes it from that database and does its calculation, and everything is visible. In order to actually get the picture of the speeding drivers, camera 2 will also need to take the picture, so it should be also visible there. The police border guard at first doesn't need to see anything. Obviously, the drivers can look at the clock when they pass the camera. They can learn when they are at the camera, so those are visible. And we assume that everyone actually knows the speed limit and the distance between the cameras, or at least can learn it if they want to. So now for the police and border guard. Since they are the ones who, in a conventional approach, would own the server, they can just look at the database and learn everything the server knows. so they see everything because they own the server. The cameras, in order to keep track of which time point belongs to which driver, which car, they should also learn what the license plate is, so it can be sent to the server to keep track and to do calculations. So the cameras see both the license plate of the speeding driver and the other driver. And to get the license plate, they obviously have to take a photo and then infer this license plate number from the photo. So again, they see additional data. Now, since in this version, the police and border guard will see everything about everyone, including the photos of the other drivers, because that's what gets sent to the server, this is not ideal. Again, we can actually make an alternative version of this, where only the entities that need to know will have access to the direct data, and everyone else will have access to some kind of protected version of this data, where they won't actually see what the data is. So for the server, again, we can just say that everything is protected. They still need access to all of this data to make the calculations, to make the decision whether a car or the driver should be fined. The cameras, similarly, they still need to get the license plate, and they still need to take the photo. This is just how cameras are built. It's very hard to actually protect the raw camera image directly at the device. You can, of course, encrypt the photo after it comes from the camera, but for some time it will, by default, have to be unprotected. But the cameras don't need to know much else, except for the time points and the license plates. The speeding drivers and other drivers, they also see exactly the same information as they saw before, their own license plate and the times when they are at the cameras. They also know the distance and speed limit. But most crucially, the third party, so to say, in the system, the police and border guard board, they don't need to see anything about law-abiding drivers. So they shouldn't receive the license plates. They shouldn't receive the times when they were at the cameras. They should learn nothing. I have marked the average speed here in red with a star as well, because in order to actually write out the fine, they should see what the actual average speed was to make sure that there was an actual infringement of the speed limit. So they should see only the average speed of the speeding driver, but not of any other drivers. So this is why it's with a star. They also don't directly actually need to see the times when they were at or the photo. This is used as evidence to show that, yes, this kind of infraction happened, but they don't actually need to see it per se. This is data that can be sent to the speeding driver, who may see it. And if they, for example, would like to argue with the decision, then they can reveal this data to police and border guard. But by default, the police and border guard doesn't need to see the data, so it should be protected when it's with them. So now, again, I would like you to take your initial visibility tables and make new tables next to them or on the other side of your paper. We have more paper if you need to. And try to similarly map out first the conventional approach, where everything sees everything mostly, and then to see what is actually will be protected in an ideal case. If you have any questions, then of course ask.
Africa must be my number one. Africa must be my number one. Africa must be my number one. Freedom, everyone the wrong. Reality, everyone the wrong. Creation, everyone the wrong. Humility, slavery is on the reign. I say we don't want no peace. We don't want no peace. All we need is equal rights now. I say we don't want no peace. We don't want no peace. All we need is equal rights now. Sons and daughters of Africa now. It's time to get yourself together to fight for our brothers and sisters in the upright countries of the world. Africa must be my number one. 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 I say we don't want no peace. We don't want no peace. All we need is equal rights. All we need is equal rights now. I say we don't want no peace. We don't want no peace. All we need is equal rights now. My brother, listen. All we need is equal rights now. That's the right. All we need is equal rights now. My brother, listen. All we need is equal rights now. What right? All we need is equal rights now. Home sweet home, home sweet home. Africa's my home now. Home sweet home, home sweet home. Africa's my home now. Home sweet home, home sweet home. Africa's my home now. Africa must be my number one. Africa must be my number one.
Okay, it seems everyone is starting to get finished, so just a few more minutes, and then you can come and introduce your use cases and visibility tables as well on stage. Okay, so it seems most of you are done already. So do we have any volunteers of who wants to introduce what they came up with in this workshop? Sure. Who wants to speak?
He's speaking. He has a voice.
Here.
All right. So we did ours based upon the study that just came out like 2 weeks ago on the fact that most cell phone data is completely unencrypted. It's hard to read on this. So the problem is that satellite data is largely unencrypted, and the paper is called Don't Look Up by Zing et al. 2025. The who is the T-Mobile customers was the primary target, but AT&T was also in there. And then they had the also talked about some government and military satellites as well, so we put them. So we have 3 total use cases on this. What is the downlink, unencrypted IP packets, and application level data. All that can be accessed. All you need is about $700, 4 pieces of equipment, and you could just randomly scan the sky and pick up all these data things to include the SMS data, voice calls, as well as internet traffic from any of the users. And then on our table, it looks a lot. We just did everything on one table for consistency, but the data objects is the SMS, and then we have the customer and the satellite, because there's 2 separate data owners on there, voice data, and then internet traffic, phone number, and then this is the satellite metadata. US and European entities have different privacy rights. So in the US customers own nothing. The satellite companies own all the data. In European countries, the customers own all the data, and the satellite providers are just supposed to provide the mechanism to transfer it. But it's, across there, opposite for that. The DOW, Department of War, we didn't talk about SMS, but we did do voice data because they were able to capture VoIP phone calls between the DoD entities, which could start culminating with up to CUI stuff, because they didn't talk about any classified protocols. If they did, they left it out of the paper. And then the internet traffic, and then the satellite metadata was visible. And then the satellite providers down here, it's the opposite of up here. They own the data for the US, and then the European do not. Visibility, we did visibility across the board. So The US cell phone customer data is visible for everything across the board except the metadata, but it should be protected. The satellite provider should protect it. We talked about the protection for the users, but it's largely up to the user to encrypt their own data on their device. And we already know that most government entities will not allow Signal to be the standard protocol for all text messages because they don't like that.
So am I understanding this correctly, that the US cell customer sees all of their own data, but...
For SMS, yes.
Yes, but the satellite part of that is protected.
It should be protected.
From the cell customer.
Yeah. Well,
okay,
it
so,
should be
so they
protected.
should get the data, but it should be in a protected form.
Yes.
Okay.
As it's in transfer and in storage
perfect.
Through the SATCOM, it should be protected at that point. And then same thing for Europe, largely. DOW, everything's visible, but it should be protected in all states. And then for the SATCOM provider, the satellite metadata was visible, but it should be protected. That's really the only difference. But pretty much everything is visible right now to all customers, but it largely needs to become protected.
So technically, it's still the exact same thing that currently everything is visible to everyone, basically, and then we need to somehow come up with ways to actually protect this data.
Yes.
In this case, it's mostly, I think, just encryption, and that would solve most of the problems.
It would. But then, like, the US doesn't want to encrypt
yeah,
message data because they can't read it then.
Yes,
right?
that's yeah, who makes the use case, right?
Yeah.
So if your problem is that you want this data, then obviously it should be always visible.
Yeah.
But for the customer, it's not very nice.
Yeah, so.
Thank you. So any other volunteers? Yeah, who was? Sure. I can help hold you. If you want.
Hello. We started from the point of the debris detection, but quite quickly, once we started making the table and had to bit simplify it to not put every stakeholder at name, we basically discovered that we have the same case as the satellite tracking that was on the first slide, basically. We just have additional object like a debris object itself that doesn't belong to anyone or does belong to itself. So basically, current situation as it is visible as much as can be detected for everyone, but ideally it could be like that there can be private data where we don't need to know the location or especially the maneuvers of the existing objects, but we need data as much to detect the collisions or to understand that what happens in the space. So started as from a different point, but then discovered that we already solved the same solution that was already solved.
So what was the original problem that you were, that's the tracking?
Actually, space debris tracking, yes.
Tracking, yeah.
And also the information regarding the space debris. That can be a bit looked from different angles because it depends also that the debris itself is not like a secret.
Yeah,
But,
that's the public thing.
but somebody may have the information about the debris, like with a higher resolution, that they are not eager to share.
Okay, yeah.
But
So in that case, maybe another stakeholders would be the actual tracking data providers, the radar owners, the telescope owners, and their the data about their equipment, how accurately they can do. That would also be a separate data object. So you can extend the same use case in a different direction as well. So instead of protecting the privacy of the satellites, you will actually start protecting the privacy of this equipment of the data providers, or how they get the data, how accurately they get the data.
But there is also a question about the motivation, like in the previous case, that if somebody is not motivated to share the data, even in the encrypted form, then there's little you can do.
Yeah, in some cases you can then start thinking about maybe you pay them for the data. So you can pay them, create a marketplace where before you pay them, you will still get some metrics about how accurate it is, maybe, but you won't actually see the image. And only after money has exchanged hands, then you will get the data out and how to protect these cases. But yeah, thank you. A great use case still.
Next
Yes,
one.
come. So who's talking?
We have a spokesperson, Leonardo.
Hi to everybody. We focused on the following problem: the voting system in Estonia. As you know, it's the only country with a digital voting system. And we were thinking mostly about rural areas of Estonia that use satellite connections to vote. While we were doing that, we found the following actors: the satellite company, which is Starlink since it's the major service provider, the voter, and the government. What are the data that we want to protect? The first one is the digital fingerprint, and of course the vote. After that, there are some intrinsic data, like the location, that are inside of the communication, even if no one owns them. And this is the final scheme that we made up. The voters owns everything, like it's supposed to be. And the government is able to, owns the final vote and is able to see in a protected way the validation of the voter and the voter station. The Cybernetica, that's the company that provides the validation for the voting system, should just see the vote in a protected way and perform the validation, while the service provider should see actually everything in a protected way. And yeah, that's it.
Great. So obviously, voting is a very complex process overall, so there's a lot of data items, but I think you got the most important ones. And if I can see it correctly, well, yeah. Just the technicality, Cybernetica isn't actually involved. We made the prototype essentially, which is now evolved, and it's in the governmental voting service.
We just wanted to
But
give you
yeah,
some credit.
yes, thank you. It's perfect. But overall, I think it's very valid. Everything pretty much should be protected, and it can be, and it is protected. So in this case, the ideal visibility and the actual how it is right now is pretty much the same, more or less. You can argue with that, of course, but yeah, I don't have a lot to say about this. Very nice work.
Thank you.
Thank you. So, left side here. Anyone want to come up and introduce what they come up with? Sure. So who wants to talk?
Okay, I guess I can talk at least from the beginning. So the use case then was the aggregation of land from Earth observation. So satellites that fly over and then look at the land. The problem is that the Earth observation data then can be used either for good or bad, right? Depending on who's going to use it. The who, of course, then are farmers, if we talk about land usage. The public, maybe they want to know the roads and things. Then we have, of course, military, both offensive and not so offensive purposes. Then we have government, local municipalities, and of course, private companies who would maybe want to use this, or the farmers themselves who would like to use the data. And what is the result of this is then, or what is it that needs to be then protected is data. But I would go one step further, it's data plus metadata at one point. Because if you combine these two, then you have yeah, you have the maps with the visual, but with additional metadata, you would have something more, right? And what would need then the privacy is then the parts of the data and also parts of the metadata. Then again, if you put information and information together, you get something more. And this is now where things get complicated. So we didn't have a consensus at the end, because it depends on a bit on who looks at the problem or who tries to protect what. Because if we take bigger countries, then they have their own satellites, they have their own government, they look at it completely differently than, for instance, we have SpaceX or somebody else who does the satellite runovers, and then they publish this information to some servers somewhere, and the use case is completely turned around, or the protection at least is turned around. But what we can say for sure is that the data comes from the satellites to the servers. All of these need to be protected, right? If it's a military who wants to use this, then either there's two ways: either they want to see everything, or they want to show as little as possible. So again, it depends on the use case. So because we didn't choose one viewpoint, we kind of got too broad, I guess, from this, so we can go either way. And for the same is for the farmers, depending on the use case as well. I mean, in some ways, the farmers want to see everything because they want to know their own competition. They want to know, right? But on the other hand, if you have a huge farm with animals and things, maybe you don't want to show your you don't want to show what you have. Yeah. So that's the point. And what else? Am I missing something?
I think that's almost pretty much.
I think that's it.
Yeah.
Yes.
Well, it's in a sense, it's a very great use case, because we can talk about a lot of things here. For example, with the farmers, as you said, they want to see their own land, of course, but they might want to protect the images from getting into competition. Other farmers to show, I don't know, how many heads of cattle you have, how much land you have, what wheat you are growing exactly and when. This is all things that should be protected, but in mostly, currently, if you use like Google Maps, for example, you see everything. Everything saves everything. But even with Google Maps, for example, the faces, if you take a street view, these are blurred. Some houses might be blurred. So there are ways to at least obfuscate the data, even on photos. And one thing that I really like, that you separated the photo from the map data items. So one is the photo that the satellite takes that includes everything around the farm, around the land that you're taking, but the map may have distilled information already. So this is one way you can also reduce the privacy infractions. You can, to the end data user, so the farmer is actually only generally interested about the map itself. They're not interested, or maybe they are interested, but they shouldn't be have access to everything around their area. So you can only give them the map and not the photo. So it's a very, very nice use case where a lot of different aspects come into play at the same time. And of course, if the farmer gets the map, should that map also include maybe the military installation next door? Obviously, military would not like that. Or should the satellite even take pictures of these areas? And it's a very open-ended problem that you have picked, and it is a complicated area, definitely. Thank you.
Yeah. Yeah.
Yes. Yes. Well, yeah, that's the metadata as well. So when the picture was taken, how often do you take these pictures, and so on. So for example, if you have your military installation, you can count the vehicles if you take the picture every day, you can start counting vehicles that are there, and so on, and how fast they are building new buildings, and so on. And with the competitive edge, even if you don't involve the military, as I said, for example, what crop is being grown, when are they making the seeding, when are they cutting the corn, and so on. So this might give the competitive edge to the farmer or anyone else. So there's a lot of this auxiliary information that can be inferred from the picture and data. And that's the hard part. Yeah.
Before a drone attack and after a drone attack, the picture has very different value.
So the picture has a lot of hidden information that might be there or might not be there, depending on what the picture is looking at. But yeah, it is, as I said, there's a lot of variables there to consider.
I would add that just if you combine information with information, then you get a result, right? So we're talking about metadata of a picture itself when it was taken, but there's like, even in this case, you can have multiple pictures from different sources, and if you combine this, then you get a completely different result. So.
Yeah, the image itself is the way to get the information. Yeah, yeah. But that gives the question: should you share the picture or the image directly with the end user, or should you do the processing and give them only the thing they want? And there's where it's very use case specific, of course. So that's where you get into a lot of these nice privacy complications that we like to discuss. Anyway, thank you. A great use case. Yep. So I think we have one last group. We can still manage to squeeze you in. There's only two of you who will you. Perfect.
So our use case was very high resolution satellite data. So we have specified an accuracy of 50 centimeters or better for the image. And I guess if we're focusing more on the use case table, then we have marked out as stakeholders the satellite owner or operator itself, then an authorized user that wants to access the data, and by other people we mean everyone that is inside of the image that was taken by the satellite, and also the data infrastructure owner who is responsible for transporting the data to wherever it might be. So for example, a ground station. And then we also put as a stakeholder, what was P? But governmental bodies, okay. I don't remember what the other two are. Yeah, we mark the owner of the location and time of a user as themselves. And the image is owned by the satellite operator. But this becomes a very subjective as to who should see what next, because the image data by itself, if it's very high resolution, can be sensitive. And so we have put that the satellite operator should operate on it in a protected form only, so they don't actually get the raw data, but only the result of it, if that's possible. It might not be possible, but maybe it is. And then authorized users should only we have visible with an asterisk to get only the data that they actually require and not anything else. And as for the other users and everything else, they don't see the data at all because they just happen to be in the image. They don't, they're just there.
Yeah, that's a very nice, a different kind of formalization of this where the people, everyone else is on the data or included in the data, but they don't actually ever see the data themselves. So that's a very a different way of looking at it, where their data is on the picture, but obviously they would not maybe want this data to be processed, yeah. But they are still included, and they don't even know that this data exists.
So they might not know that they are on the data itself. And the same thing applies to this government body, which could be like the owner of a land area. So,
in a sense, it's very similar to the last use case where you're using image and map data. So all of the considerations there also apply here. I like that you also included the time there. So that's also, if you take multiple pictures, if you have a frequency, you can start tracking people as well, do all kinds of different things with this. And this is something that, again, there's so many offshoots from this core use case, let's say, where you can, it very much depends on who is actually, who is the end user of the data, what is the problem they're trying to solve, and so on. So, yeah, great, thank you. So, as we can see, mapping out these visibility tables of who sees what and who should see actually what is a very complicated process. There's a lot of things to consider, a lot of different use cases to consider, a lot of stakeholders and their wishes to consider, and so on. But what do we actually need to do to actually get to this, from this conventional approach to the actual ideal approach that you have now all designed? One solution is to use privacy-enhancing technologies, what exactly as the name says, enhance the privacy of some processing. The other one is confidential computing, which is a subset of these privacy-enhancing technologies. By understanding these secure computing techniques and privacy-enhancing techniques, you can start more and more noticing these kinds of use cases as you map today, and to find what are the problem areas. And if you know how privacy and privacy-enhancing technologies, what there are, which ones there are, and how they help, you can start thinking about these use cases in a different way. You can start pushing for more private solutions. So instead of having these fully visible visibility tables, you can start getting closer to the ideal ones in practice. So privacy-enhancing technologies are exactly as the name says. They connect to these privacy goals that they are trying to enhance in some way into one of these branches. You have the whole umbrella of privacy-enhancing technologies, but you also have these intervenability technologies, transparency technologies, unlinkability technologies, exactly each for one end of this green triangle, these privacy goals. And each one of them works in a slightly different way. With the intervenability technologies, it's somewhat easy. These are all your cookie banners, your privacy dashboards, where the user can just say how they want their data to be used or not used. And this is generally considered to be conventional engineering. Transparency technologies are often similar, where you use logging and auditing to make sure that everything that is happening is tracked and logged, and you can trace back to who actually did started the process and who used the data. This is also somewhat well used in the conventional computing. Unlinkability technologies are a slightly more or less known beasts. This can also be separated into three large fields. There's the privacy of data in information systems. This is technologies like encryption, for example, where you are actually trying to protect the data from being used in one or other way, from any other third parties who are not authorized to access the data, to protect the data itself in these systems. But we also have privacy of identity and authentication. So, for example, with one use case we had here was the internet voting. You want to protect the privacy of the identity, so who voted, who went and actually gave a vote, and who abstained from giving a vote, for example. You still want to protect the privacy of the individual, the identity, and to also maybe, if you think about authentication, you may want to log into a service, but you may not want to show that you logged in. So you want to authenticate without actually the service maybe knowing who exactly it is who logged in, just that they are authorized to access it. On the privacy of communication and transactions, these are things like onion routing and Tor and that kind of things. where the fact that you communicated with someone else, that is the thing that is protected. So you may not want to anyone else know that you communicated with your friend Bob, but you still want to communicate with them. So this is the class of technologies that helps to protect that. And all of these have multiple ways to achieve the privacy, all with their own goals, with their own limitations, with their own deployment models, and so on. But I will quickly, with the last 15 minutes, go over the privacy of data and how we achieve this. Mostly this is through the concept of confidential computing. So conventionally, the top row here is how it normally works, where everything is nice and encrypted and protected from the user to the database. And then when some kind of service provider who's offering to do your computations or process your data, they will take the data from the database and then they will remove the encryption. They will unencrypt the data, they will do their calculations, get some result, and then maybe they will re-encrypt the output and put it back into this database. But all the time that they are using the data, it is unprotected. Someone who is standing behind this analyst who is doing your computations, they can look at the screen and see your data. If the computer where they're doing their work is hacked some way, then this data can be exfiltrated at that point in plain text with no protections. Of course, there are ways to limit the attacks and so on, but at the core, the data is unprotected while it's being used. Confidential computing tries to now protect this middle part, where the data is also protected during use. It's protected in use without ever removing the protections. So the data, all the way from the data owner to the data analyst at the end, it is never, the protections are never removed. And in that case, the attacker really doesn't have any way to access the data unless they are the data owner or the data analyst or at those points. One of the simplest ways to achieve this confidential computing is trusted execution environments. These are essentially limiting the area of attack. So when conventionally you have your whole computer, they can come from read your memory, they can look at your screen and so on, then trusted execution environments try to limit this area where the data is unprotected to a very minimum. And in general, if we take the example of Intel's software guard extensions, Intel SGX, which is one implementation of trusted execution environments, they have a physical area in your CPU chip that where only inside this very little area that is tamper-resistant, they unprotect the data. But everything else on the CPU, the memory lanes, the memory RAM itself, everything is still encrypted. And this little chip has all kinds of fancy cryptography to make sure that the code that is running there, that is doing the processing, that is exactly the same as you said or want it to be. So even if an attacker gets access there, they can't change the process. And you can authenticate that this exact environment in this exact CPU, that this is the one that you're talking to, that you're sending the data to. The good part about this is it's very similar to normal computing. It's easy to somewhat easy to transfer your applications, your programming flows into these trusted execution environments. And they have pretty much native performance. I think it is about 10% slower than just regular computing. But one peak issue here is that at some point your data is still unencrypted. And you need to really trust the hardware manufacturer. So in the case of Intel SGX, you need to trust Intel that they haven't put any backdoors in your software, in your hardware. And of course, the side channel attacks are very hard to mitigate. There have been attacks to trusted execution environments where they actually measure the power levels of the CPU, if it uses more power or less power, and infer some data through that, and that kind of attacks are very, very hard to protect against. A slight slightly more advanced version of this is fully homomorphic encryption. So instead of relying on hardware, you will rely solely on math and cryptography. This is one subset of encryption methods where you can actually perform some operations directly on the encrypted data. So with the example here, you can encrypt your secret X, and you can encrypt your secret Y. You do some operation on these encrypted ciphertexts, and the result of this should be exactly the same as if you first added up your X and Y and then encrypted the result. So you can do the addition directly on the encrypted data and have the same result. It is the so-called holy grail of secure computing, confidential computing, that would allow you to basically off-source all of your computations to some cloud environment, and the service provider would see absolutely nothing because everything is encrypted all the way through, and only you hold the key. But the problem with this is that the current existing versions of fully homomorphic encryption are very, very, very slow. So if I said that trusted execution environments had roughly 10% overhead, then fully homomorphic encryption has in the order of magnitude of millions times slower than regular computation, maybe even more. But for some specific use cases, it does work. For example, it's been used for private set intersections and looking up data privately. But as I said, it's very slow and it requires a lot of computing power for even trivial things. But it fits somewhat nicely into existing systems. As I said, you can just lift your computation in the cloud if you implement this. But it is also somewhat complicated to have multiple users. So if you have the key, then you cannot really join this data with someone else's data because you can't have their key. So you can only do operations on your own data. A middle ground between these is something called multi-party computation. This is, again, a fully mathematical cryptographic approach where inputs can be split into pieces or encrypted, and each piece of this data is sent to a separate distributed server. So if we look at this picture here, the top one has 3 sections, black, orange, and blue. The black piece goes to the black server, the orange piece goes to the orange server, the blue piece goes to the blue server. And each of these servers then runs the computations on their own, maybe communicating with the others using special protocols, but never actually revealing the original share of the data. There's one piece of data that they get. And only at the end of the computation, when you get some kind of result, only then you will, the output party can reconstruct the secret. They can put the pieces back together and see what the result is. These general approaches with this include a lot of math. They are still significantly slower than native computation. And it requires you to actually have these 3 servers that do not collude. So if all of these 3 servers were owned by a single service provider, then of course they see the data, they can take out the memory dumps and put the data back together, breaking the security. But if you can find a nice deployment where you have these 3 servers that are mutually distrusting, that want to protect the data as well, for example, if they are a data owner themselves, the input party, then this is a place where multi-party computation works really nicely. And this is what we at Cybernetica really like to use for a lot of use cases. As I said, it still needs a lot of math to do these protocols on these computation parties, but it's still a lot faster than homomorphic encryption. So as I said, homomorphic encryption was in the order of 1,000,000 times slower than multi-party computation is 10 to 100 times, depending on the exact use case. And it is very, or somewhat easy to program it as well. It needs some work to make your normal code work in a multi-party setting. You need to do some adaptation to make sure that it works fast. But in general, it's a general purpose programmable model. So all of your use cases can be implemented with multi-party computation. And as I said, finding these 3 mutually distrusting servers is the hard part. For something totally different, we have zero-knowledge proofs. So whereas all of these previous technologies are intended to use for general purpose programming, then zero-knowledge proofs are very specifically interested in proving some statement. For example, if I want to prove that I'm over 18 years old without revealing my birth date, then I could use zero-knowledge proofs for that. So these are systems where some party wants to prove a statement to a verifier without revealing any actual data of how this statement or why this statement is true. They have three main properties. One is completeness, that if the statement is true, if I am over 18, then the verifier will actually accept this. They won't say that, okay, but I still don't believe you. They will have to accept this. Soundness, so if the statement is false, if I'm trying to lie, then the zero-knowledge proof system should actually not work, and the verifier will not be convinced. So in that case, they should know that you're lying. And finally, zero-knowledge, that the verifier should not actually find out what the underlying data is, except that the statement is true. So here is a quick table to summarize. Trusted execution environments are very fast and easy to deploy, but you need to trust the manufacturer. That's the main caveat of this. If you cannot trust the manufacturer, if you don't have this secure element, then it's somewhat tricky to convince yourself that this is secure. With fully homomorphic encryption, there are no real requirements. It is the holy grail of secure computing, if it could be done fast. But in fact, it is very, very, very slow, and it is somewhat quite tricky to actually transform your use cases to this, to the fully homomorphic encryption setting. MPC is somewhere in between. It has some overhead, but not as much as homomorphic encryption. But it requires you to find these mutually distrusting parties to distribute your secret shares to, which can be challenging, and in some use cases, it is impossible even. For zero-knowledge proofs, their output can only be yes or no, so you're only proving some statement to someone else. But they take some time, but not unfeasibly slow, and it still requires quite some work to actually deploy and use these zero-knowledge proof systems. A lot of these have already been used in practice as well. For example, trusted execution environments have been used even at Cybernetica to do AI recommendation systems, where user data is, for some reason, needs to be protected, and to train the AI and or to do inference on AI. For example, if, think about medical recommendation, where you need to give guidance to the doctor of what to do next, but patient data is confidential, then maybe you can use trusted execution environments to do that. But with multi-party computation, this is one of the examples that we had today as well. The satellite trajectory data is split into 3 pieces, and we have these distributed servers that run these collision probability calculations. And at the end, the satellite owners will learn if their satellite is going to crash with someone else or not. Fully homomorphic encryption is slightly less used because it is as slow as it is. But for example, it's often used for checking if some data is in a known list. For example, malware detection. You need to check if a piece of program is malware or not, and to do this, you use a reference list. But the data itself, the program itself, might be sensitive, so you don't really want to share that. You can use fully homomorphic encryption to do some kind of fingerprinting, and then check against the list. With zero-knowledge proof, this is also a use case done by Cybernetica, is that electric vehicles get subsidies from the government if they are driven some amount of kilometers within Estonia. But of course, the location data, GPS data of the vehicle is confidential. You don't want everyone to know where you have driven and when. But with zero-knowledge proofs, you can make sure that you have driven this X kilometers in some time frame without actually revealing where and when you drove. So these are really usable things, but in order to use them, you need to actually start by defining these use cases and designing what can be visible, what cannot be visible, what is needed for the processing, what is not needed for the processing. And only once you have actually defined your use case, then you can start selecting which of these technologies is the best for your use case. And this is where I will end today. Hopefully you all learned something about trusted execution and secure computing techniques and about how to actually think about privacy in your own systems. Thank you.